Thanks, Tim. Thanks, everyone. Thanks to the University of Michigan. I'll apologize ahead of time. They had me doing a lot of talking yesterday, and my voice not quite up to it. So I'm hoping that you'll be able to hear me during this talk today, because we have some fascinating things to talk about. Quantum mechanics is this weird position in physics today. It's our most successful theory of physics of all time. It is the way the universe works, as far as we know currently. Of course, we might find out something better tomorrow, but right now, the best theory we have. You can't understand the universe without quantum mechanics. At the same time, physicists don't know what quantum mechanics says, which is strange, right? I mean, there might be individual physicists who know what it says. I know what it says, but not everyone agrees with me. This is very frustrating. I did write an op-ed for the New York Times a few years ago complaining about the fact that physicists don't understand quantum mechanics, and I was pleasantly surprised that only one of my colleagues emailed me to say, "I understand quantum mechanics, what are you talking about?" But I do think that we can understand quantum mechanics, and that's the crucial thing. It's not that it's some ineffable mystery that we can't reach. We just have to be open to truly changing our view, our picture of how reality works. It's a radically different picture than what we had before quantum mechanics came along, and I want to push some of those implications front and center here. So here's how radical it is. When you look around in the universe, there's a natural way to describe what you see, namely as stuff arranged in space. So we have space, it's three-dimensional, right? We have stuff, we have tables, we have floors. Here's a photograph of a subset of the universe. Stuff arranged in space, in this case, is a chair in a room, right? And even that idea that what the universe is fundamentally is stuff arranged in space is not true according to quantum mechanics. It's what you see, it's what you think there is, but it's not what is actually going on. The reason why quantum mechanics is hard is because it posits that what we see is not what there is. Reality is much, much richer than that. One way of thinking about it, as we'll see, is that reality, the whole thing, is a superposition, an additive combination of many different versions of stuff arranged in space. So we have access to just this infinitesimal sliver of all of reality. This rubs us the wrong way, and we go into denial about it, and that's why it's very hard to accept what quantum mechanics says. So what I'm going to suggest, arguing after many other people preceding me, is that reality can be divided up into individual worlds, each one of which looks like stuff arranged in space. And this simple posit, I will argue, makes sense of the mysteries of quantum mechanics. But to get there, I have to convince you that we should think about quantum mechanics in the first place. So let's do a little history. Like, physicists are terrible at doing history, by the way, because we forget all the messy parts and the mistakes, and we pretend that it's a beautiful sequence of brilliant deductions. And that's what we're going to do today, brilliant deductions. You know, if you were the early 20th century, it was a very exciting time to be a physicist. We were putting together this picture of the world made of atoms. In the 19th century, chemists, we have to give them credit, they acknowledged the existence of atoms before physicists did, but they also made a mistake. They thought they were indivisible, and the physicists instantly started dividing them. So by the early 20th century, we knew that an atom was a nucleus, a heavy, positively charged thing. Now we know it's made of protons and neutrons. And then electrons orbiting around the nucleus. So a picture like this is what you will very often see. It's the symbol of the Atomic Energy Commission that we used to have in the United States and so forth. It's the icon of physics. It's also clearly wrong. This can't be what atoms are like. We knew that almost the moment that this idea, the Rutherford atom, named after Ernest Rutherford, almost the moment it was proposed, we knew it couldn't work. Because think about all the light that we have in this room. Where does this light come from? Maxwell, James Clerk Maxwell in the 1800s, explained that light is an electromagnetic wave. We have an electrical field, a magnetic field waving in empty space, that those waves move at the speed of light. That's what we see as light. So if you take a charged particle like an electron, it has an electrical field pointing at it, and you move it, the field adjusts, and the adjustments ripple out at the speed of light, and that is light. That is radiation. If you had an atom like this, like a little solar system looking thing, those electrons orbiting the atom would be moving and therefore sending out electromagnetic waves, and therefore losing energy, and therefore spiraling in to the center of the nucleus. You can calculate this. It's kind of fun. If you're a beginning physics student, you can say, how long should it take for an electron orbiting a nucleus to just spiral into the middle? The answer is about 1/100th of a billionth of a second. This is an experiment. Don't accuse me of not doing any experiments here Saturday Morning Physics. Let's do that experiment. There, we did it. It didn't happen. Our atoms did not collapse, okay? We would have noticed if this were true. So we have, on the one hand, an attractive picture. On the other hand, it doesn't work. So there's some fundamental problem. And there were various steps towards solving the problem. The solution that eventually worked was sneakily radical. Like when physicists do come up with radical new pictures of the world, they creep up on them. They don't just say, it's not like some genius comes out of the cave and says, aha, a new paradigm for understanding reality. It's step by step. So the step that worked in this case is to say that electrons are not particles. They're waves. They have a profile. Rather than being a point with a location, there is a function over all of space that has a profile that can look like these different shapes. Again, if you're a chemist or you take chemistry, you've seen these shapes. These are the orbitals that electrons can fall into in atoms. And the thing is that there are only a finite number of shapes, or at least a countable number of shapes that you can write down. All of these shapes are associated with different energies, and there is a minimum energy shape. It's the one in the top left, right there. What is the chances this can work? Right there. Minimum energy that an electron can have. And it's not sitting on top of the nucleus, it's spread out. So this answers why matter is stable. Matter is stable because electrons are not little points orbiting like planets in a solar system. They are waves that have certain shapes they can fall into. Good, huge progress. It was pretty radical to say that electrons are waves, not particles, but the stability of matter is an important consideration. Even better, we can invent an equation that these waves solve. Do not be alarmed. There will not be homework at the end of the lecture. You do not have to solve the equation, unless you're a physics student, in which case solving this equation is like half of the time you spend in the world. This is the famous Schrödinger equation. The Greek letter capital psi is what we now call the wave function. This is the most boring name in the world for the most important thing in the world. That little electron has a wave function. It's just a number at each little point in space, technically a complex number, but that's not really relevant. Schrödinger writes down this equation. Again, you don't need to know the details, but the spirit of it is, on the left-hand side, you ask how much energy is in the wave function. On the right-hand side, you have how rapidly is the wave function changing. So Schrödinger's equation is basically a quantification of the idea that the more energy the electron has, the faster its wave function is changing. Good. Physicists love this. There's an equation we can solve. We can write down homework problems for our students. It's paradise for physics. All you have to do is believe that electrons are waves, not particles. There's one little problem with this picture, that when you look at the electrons, you don't see waves. You see particles. This is literally a little video of a radioactive substance in a cloud chamber giving off particles of radioactivity. And what you see are not like big puffy clouds. You see trajectories, little lines, as if what is escaping in the radioactive decay is a particle with a location moving away from the substance. So that's a puzzle. That's a real puzzle now. Now we're stuck with something. We had simple puzzles before. This is a deep one. It's almost as if, in order to explain both what we see and the stability of matter, we have to say that electrons behave like waves when we're not looking at them. When we're not measuring them, We describe them as waves, there's a function, there's an equation, all good. When we measure them, suddenly they look like particles. Of course, this is crazy talk, right? How in the world could the fundamental nature of reality care about whether you and I as human beings are looking at it or not? We like to think as physicists that reality exists outside of our observation and measurement. So this is a puzzle. We assembled the world's greatest minds at this wonderful conference in 1927, the 5th Solvay Conference. Literally, probably never a higher concentration of super smart people has ever been assembled. You have Einstein, there's Marie Curie, there's Lorentz, there's Dirac, there's Heisenberg and Niels Bohr and Pauli and all these great people. And they were tasked with the job of reconciling. Why is it that it seems like electrons behave like waves when you're not looking and particles when you are? So they thought about it. They had a few fine Belgian ales. It was held in Brussels. And they came out and said, all right, we've got it figured out. Here's the answer. The answer is that electrons behave like waves when we're not looking at them, and they behave like particles when we are. And this is what we teach our students today. And if the student raises their hand and says, well, what do you mean by look at or measure or observe? I don't understand why nature should care about that. They're told to leave the physics department. So what we teach our students is a recipe, not an understanding, not something that makes perfect sense, but something that fits the data exquisitely well, which is to say when you're not looking at an electron or anything else in the universe, it is described by a wave function. So here's the function psi as a function of x and y, position in space. But then when you measure it, it collapses. So the wave function changes suddenly to be localized at a point. And one of the things that rubs you the wrong way about this is you can't say where it will collapse. You can say the probability that it will collapse to different positions, but the fundamental rule that we teach our students is it randomly collapses, more likely to collapse where the wave function was big than where it was small, but there's a chance of it collapsing any of those places. So when we teach quantum mechanics, unlike any other theory of physics, we need to teach two sets of rules. And I swear, I'm not making this up. I'm just being honest about it. There's one set of rules for how nature behaves when you're not looking at it, and another set for when you are. When you're not looking at it, systems are described by wave functions. They always obey the Schrodinger equation. As soon as you measure something, as soon as you look at it, the wave function collapses, and there's a probability that depends on the value of the wave function. In fact, the probability is the wave function squared. This is not like classical mechanics. It's not like, you know, my friend always looks so good, but when I try to take a picture of her, like she doesn't look as good because I'm measuring her and changing her state. That's not what it is. This is a fundamental thing about reality. In classical mechanics, you could, in principle, measure things very carefully and get exactly their values. There's no barrier between you and the truth of reality. But in quantum mechanics, there apparently is. So this is called the Copenhagen or the textbook interpretation. It is what we teach our students, honestly, and you're not encouraged to question what is really going on. That's too bad, because this is clearly nutso. I mean, it's not that it doesn't work, but if you're trying to claim that what we're interested in is a fundamental theory of reality, it's not that this is wrong, it's just that it's not even defined. It's not even well posed. It's clearly unacceptable as a fundamental theory of reality because we haven't said what it means, really. So we can put our fingers on two problems. One is called the measurement problem. This is pretty obvious. What do you mean, measure? When does a measurement happen? When exactly? Does it need to be a conscious creature? Can I measure things when I'm asleep? Can a robot measure things? Can a cat? Can a single photon measure things? Why does it happen randomly? Is consciousness somehow involved? People talked about all of these things, and sometimes they still do. So this is the fundamental issue. It's not that the theory is wrong. It's that it's just too vague. It's not a theory. We have to do better.